Hello students, welcome back. Now we are going to explore one more feature that is available on our Basis 3 board, and that is 7 segment display. So in this video we are going to talk about that what is a 7 segment display, how can we code to access the 7 segment display available on the board. We are going to implement a 4-bit adder and we are going to demonstrate it on the Basis 3 board. So let us get started. So first of all, we should know that what is a 7 segment display. A 7 segment display is basically a combination of 7 LEDs which are arranged in a specific shape so that we can generate the different numbers using these LED patterns. Each LED is independently controlled and we can switch on or off any one of them and we can generate different patterns. It is inbuilt on Basis 3 FPGA. There are 4 7 segment displays which are available. We are going to use only one of them. Now there are two types of 7 segment displays that are available in the market. One is common cathode and one is common anode. On Basis 3 we have common anode type of display. So what are these two types? We'll talk about them in detail. But before that, let us have a look at the display patterns that can be generated using the 7 segment display. So you can see that there are 7 LEDs, and if I switch on few of them, we can generate numbers like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can also display hexadecimal numbers A, B, C, D, E, F. So these patterns can be generated. Now we should know that how do we generate it. The important point is the internal connection. As you can see that there are 7 LEDs, but on the 7 segment display IC there are 10 pins. 2 of the pins, that means pin number 3 and 8, they are connected together, and other 7 pins, they are used for each LED control. There is one more LED which is for displaying the decimal point, which is DP. Now, how do we illuminate these LEDs? That will depend whether it is a common cathode or common anode. In common anode, what we have done, we have connected the common pin, that means pin number 3 and 8, to high voltage, that is 5 volt or 3.3 volt, whatever is the operating voltage of our system. Now if I give logic 0 to cathode, then the potential difference will develop across the LED and LED will glow. That means if I give input as 0 to any of the pins A, B, C, D, E, F, G or DP, that particular LED will glow. And if I give input as logic 1, then that particular LED will be off, because the potential difference between 1 and 1 is 0, the LED will not glow. In common cathode, the idea is completely opposite. All the cathodes, that means the N side of LEDs, are connected to ground. So if I give inputs A, B, C, D, E, F, G as 1, then the LED will glow. Now let us remember that on a Basis 3 board we have common anode type of display. So how do we generate different numbers? So let us say I want to generate 0. So in that case I will keep A, B, C, D, E, F as 0, because these are the LEDs that I want to glow, and I want to keep the central LED as off, so I give 1. Now we can follow this and generate any number. If I want to display 1, I will switch on B and C by providing 0 at B and C, and others will be 1, and it will follow for rest of the numbers. Now, how do we code it? That is also an interesting question. We are going to use 7 bits as our output, not the 4 bits as our sum, because now we want to control 7 different LEDs. We will use case statement. This is the code for a regular 4-bit triple carry adder that we have designed earlier as well. We are having 4-bit number A, 4-bit number B, input carry is C, and output is a 4-bit number sum along with the output Cout. We used 3 wires C1, C2, C3, and we used the method of module instantiation, and we had mapped 4 full adders to make one 4-bit adder. Now what we have done, we have modified this code slightly, and here is the code. Initially, the biggest change will come in outputs. The output is not going to be 4-bit of sum, but we will take 7-bit of segment. Then 4 bits of anode. This is used to decide that which of the 7 segment will be used. Cout we will still show on LED. So instead of 4 bit of sum, we are using 7 bit of segment and 4 bit of anode. Now we declare a 7-bit register segment, and I declare 4-bit sum as a temporary variable, which is wire. C1, C2, C3 are already there. So this code is as it is. I have not changed anything. That means the sum, this S, is getting all the 4 values. Then we say assign AN equal to 1110. That means the rightmost 7 segment display will be active, other 3 will not be active. Then we say always at the rate S. S is what that contains our information on sum value. Case S 0000. Now we have to write A on this side, B, C, D, E, F, G. So this is very important that A will be here, B, C, D, E, F, G. Let us have a look at the truth table again and see that what is written in the code. So have a look carefully. When the input is 0000, my sequence is 6 zeros followed by 1. What I have to do in the code is just flip this, and I will write 1 followed by 6 zeros. So that is one major thing that you have to take care while mapping. What is the reason? Because here A is basically my least significant bit. I am writing it first, but when we write it in Verilog, least significant bit should be on the right hand side, not on the left hand side, and that is the reason we are flipping it. Now we will write all the 16 cases. For every hexadecimal number, we are going to write that what is the corresponding 7-bit code. The next step is to write a constraint file. We can go to the sources and create the constraint file. One thing that we have to take care that whenever we create the constraint file, only one constraint file should be active. So if there are 2 files that are active in your project, please make sure that the irrelevant files which are not attached to my current source are disabled. So now in the constraint file, what we have done, I have used 4 buttons. These are the switches for input A. The rightmost buttons are used for input A. The leftmost four buttons are used for input B of 0, B of 1, B of 2, B of 3, and one of the central switches is used for input carry. So I am using 9 switches. Then I am using one LED for my Cout. Then we go to 7 segment display, and here I did not change anything. The only thing which I have done is removing these comments. What I had done earlier, I had taken the name of my output variable, the port, as SEG, which is exactly the same that is written in the constraint file already. So I did not have to make any changes here. So seg is used as it is. I just uncommented these 7 into 2, 14 lines. Then for anode activation also, my port name was same, AN, and I have to just uncomment these. These are the few things that we learn with experience. That means we don't have to spend more time in coding. We can use the same variable name. Now the coding is done. All you have to do is run synthesis, run implementation, generate bit stream, and then open the hardware. We have opened the hardware manager and we are going to program our device. On the right side you can see that our FPGA board basis 3 is connected with the USB wire and it is displaying numbers 0 to 9 on all the 4 7 segment displays. Now we click on the program button. So now the device is being programmed and you can see that the first 7 segment is displaying the number 0. Now let us check all the cases in detail. Now we are going to define the inputs through these 4 switches. These 4 are for input A, these 4 are for input B, and one is for the carry. Our output will be displayed on this 7 segment display and the output carry will be displayed on this LED. So first of all I am giving A as 1 and now you can see 0 plus 1, the answer is 1. Now I make it as 3 and 0 plus 3, it is 3. Now I make 1 on this side, so 1 plus 3 is 4. Now I make 4 more, so 4 plus 4, that means 8. And now we will add more. So let us add 8 more. So now on this side I have 11, on that side I have 5, so answer is 16. That means carry is 1 and sum is 0. 1 followed by 4 0, that makes 16. If I add 4 more, now I have 16 plus 4, this is 20, and we can check for any other combination as well. So students, now we know the complete process of FPGA implementation. We have a module test coming up and then we will go to the next module where we are going to talk about different projects that can be implemented using the VLSI techniques. Keep learning. Thank you.